Section 4.5, our objective today is I can prove triangles congruent using other methods. Our tools so far that we have used for proving triangles congruent are three postulates. The side-side-side postulate. So if corresponding sides of congruent triangles are congruent, then we can say the two triangles are congruent. And we've also done the side angle side. And in the side angle side, we need to have two sides and the included angle of one triangle and two sides and the included angle of another triangle. Then we can say the triangles are congruent. And we've had the angle side angle postulate, which if we have two angles and the included side of one and two angles and the included side of the other, then the triangles are congruent. And those postulates work for any kind of triangle. Doesn't matter which one. Today we're going to learn two theorems, one that works for any kind of triangle and one that only works on right triangles. So our first theorem is called the angle side theorem. Okay? And it says if two angles and a non-included side, and that's the key, it has to be a non-included side of one triangle are congruent to corresponding parts of another triangle, then the triangles are congruent. Okay, so here's what it says. Okay, so we have two triangles, A, B, C, and D, E, F. So in triangle ABC, I know angle A is congruent to angle D. Angle B is congruent to angle E. And I need a non-included side. So BC would be a non-included side, and EF would be a non-included, the corresponding non-included side. So if angle A is congruent to angle D, and angle B is congruent to angle E, and segment BC is congruent to segment EF, then triangle ABC is congruent to triangle DEF. That's what the theorem says. Now, could I have used AC congruent to DF? Are AC and DF non-included sides? Yes. So I could have, in this case, if I knew that AC was congruent to DF, I could have used that set of sides. Okay. Then our second theorem only works for right triangles. So let's kind of review what we know about right triangles. So remember, in a right triangle we have one right angle, and we'll call this A, B, C, and we know that the sides of the right triangle are called the legs, and then the side opposite the right angle has a special name. Remember, it's called the hypotenuse. Okay, and so that's important because in the second theorem, we have to have the hypotenuse and one of the legs. And notice that the legs are the segments that are perpendicular to each other. Okay, so the two segments that are perpendicular to each other are the legs, and the segment that's opposite the right angle is always the hypotenuse. Okay, now the following theorem only works on right triangles, because right triangles are the only ones that have what we call a hypotenuse. And this is called the hypotenuse leg theorem. And we abbreviate that as the HL theorem. Okay? And it says, if the hypotenuse and a leg of one right triangle are congruent to corresponding parts of another right triangle, then the triangles are congruent. Okay, so let's look at some examples here. Okay, so example 1. Okay, this is parallel to this. This is a right angle, and this is a right angle. And so what can we determine? Well, this line is parallel to this line, so then this is a transversal. So we can say that this angle is congruent to this angle because those are alternate interior angles. And we can say that this angle is congruent to that angle by vertical angles. But can we conclude anything about the sides? Because remember our tools: side, 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 angle, side, angle, side, angle. Those are our postulates. And then we have angle, angle, side, and we have the hypotenuse leg. So all of those require that we know at least one of the sides, and we don't. So this is no conclusion. Okay, so we cannot say that those two triangles are congruent. Example 2. Okay, so in this example, I have this triangle and I have this triangle. And notice that these happen to be right triangles. And I know that this side is congruent to that side, so I have the legs. So could I get the hypotenuse congruent to each other? And yes, by the reflexive property, I can say that segment's congruent to itself. So by the HL theorem, HL theorem, I can say that the two triangles are congruent. Okay, example 3. Okay, and in this picture, I know this is congruent to this, I know this is congruent to this, and I know this is congruent to this. Okay, so notice my two triangles are this one and this one. Okay, so what do I have? In the yellow triangle, I have this angle and that angle and this side. What's the relationship between those? So I have two angles and a non-included side. So do I have the same thing on the other one? Do I have two angles and the non-included side? Yes. So I could use angle side theorem. But also notice that they share this side. They share that side. And so by reflexive property, I can say that they're congruent. So then I could get the side angle side postulate. I'm sorry, wrong one. Angle side angle postulate. And I also notice this is I have side angle side. So I could also say they're congruent by side angle side. So many times there's more than one way to prove triangles congruent. Let's do one more. Okay, and so with this picture, I know that this is parallel to this, and then this could be a transversal. So therefore, I know that this angle is congruent to, congruent to this angle. And by the same token, notice that this could be a transversal. So I know this angle is congruent to this angle. Okay, so I could use angle side angle to say that they're congruent. Okay, but notice that I could also get vertical angles here, which would give me two angles, which would be, oops, I need another line there. Okay, which could be this angle and this angle. So this angle and this angle, and then I have the non-included side. So I could also use angle side to say that those are congruent. All right, let's do a proof now. So our given is that angle B is congruent to angle D, and that segment BC is parallel to segment AD. And I want to prove that segment DC is congruent to segment AB. Okay, and here's my picture. Okay, and this is A, B, C, D, and I have segment AC, and I know that this is parallel to this. Okay, so what I want to get is that DC is congruent to AB. Okay, so I need to get those congruent. So I need to get triangle ABC congruent to triangle ADC. Okay, so that's my goal, is to get those two triangles congruent. So here's my statement, and here's my reason. Okay, so number one, angle B is congruent to angle D. So I know this one's congruent to that one. So I have angles. And I know that BC is parallel to AD. And I know all that because it's given. So if this is parallel to this, then I know let's see, I know that this would be a transversal. So that means that angle CAD, which would be this angle, and angle ACB, which would be that angle, have to be congruent, okay? So I can say angle CAD is congruent to angle ACB. And that is because two parallel lines cut by trans, then alternate interior angles congruent. Okay? So notice now that I have two angles of one congruent to two angles of another. So I either need the included side or I need a non-included side. And notice that I can get this congruent to itself by using the reflexive property. So I know AC is congruent to AC, okay? And so then I have two angles of one and the non-included side, and two angles of the other and the non-included side. So now I can say the triangles are congruent. So triangle ABC is congruent to triangle CDA. Whoops. And that is by the angle side theorem. Okay? And so then if the triangles are congruent, then their parts have to be congruent. Corresponding parts have to be congruent. So then I can say DC, segment DC is congruent to segment AB because corresponding parts of congruent triangles are congruent. And we're done. We have proved that they are congruent.